Our goal in this tutorial is to give you a broad understanding of how sensors work. Also, we will not go into the deep details of the physics of electronic components or equivalent models. But we will go into the functionality of the sensors enough to understand how the sensors can be used. In this video, I have reviewed the 10 most common passive sensors and introduced various circuits. I have done a detailed tutorial on these components on my YouTube channel, and you can refer to the videos for each one. What are passive sensors and how to use them? Passives in general within the electronics community are devices that do not drive or transmit power or signals. Passive sensors do not control electricity directly and do not require external power sources to accomplish control of an electrical signal. Similarly to an active sensing, passive sensing shall be examined through the capacity of the sensors. Identification of the types of these sensors have to come from the essential qualities they possess, which is that these sensors are designed to react to natural emissions produced in the vicinity of their environments. This means that passive sensors need no additional powering, as these do not create a special field of energy, but rather respond to changes of physical quantities within the spectrum of energy around them that is pre-existing or created independent from them. Passive sensors are famous for their responsiveness to vibrations, light, radiation, heat, magnetic field, etc. Some examples of the technologies and sensors used as passive sensing systems are thermal, photography, electric field, seismic, chemical magnetic field sensing devices. For more information, refer to the video, Active and Inactive Parts, on my channel. As we know, both of these parts are variable resistors with temperature, but they are opposite to each other. PTC is directly related to temperature, but NTC is inversely related to temperature. That is, as the temperature rises, the resistance of NTC decreases, but the resistance of PTC increases. When the thermistor is cold, resistance is high and current cannot pass through. When warmed, resistance falls and current passes through. A simplified circuit is shown. When the thermistor is cool or cold, the LED should not light because of the high resistance. However, warm up the thermistor by blowing warm air from a hairdryer across it. This should warm it sufficiently that in a few seconds the resistance will drop and the LED will light. The preset resistor can be turned up or down to increase or decrease resistance. In this way it can make the circuit more or less sensitive. In the next circuit, the preset resistor and thermistor have swapped position. The circuit is now a cold sensor. The LED illuminates when the temperature drops to near 0 degrees. It could be used as an ice sensor for a car. You see another circuit designed with 2 transistors that is a cold sensor switch using an NTC thermistor. This circuit is very sensitive and can easily be used to sense cold or low temperature. It can activate any device connected with the relay on your desired coldness low temperature. The temperature sensing is done by an NTC thermistor. When temperature increases, its resistance decreases, and at low temperature, its resistance is increased. The operating voltage of this circuit is 9 to 12 volts. A 100K thermistor is used to sense the temperature, and 22N4401 NPN transistors are used as switches in this circuit. Initially, at high temperatures, the resistance of the thermistor will be minimum and it will keep the circuit deactivated. When the temperature is low, thermistor's resistance is increased and it will activate the transistor. The transistor Q1 will now give 0.7 V at the base of the transistor Q2, which switches on and activates the relay. A 10K variable resistor or a potentiometer is used to adjust the circuit to activate the relay at your desired low temperature. The relay used in the circuit should have the same value as the input voltage. Since we have a relay switch at the output of this circuit, you can connect any load like a fan, etc., to operate it at your desired temperature. In this part, we are making a project of a simple temperature sensor circuit. This circuit activates an LED when it senses or receives heat, so you can also call this circuit a heat sensor circuit. Apart from its uses, if you are a beginner who just wants to make an easy and interesting project, this circuit is ideal for you. This circuit is very sensitive to heat since we connected two transistors as a Darlington pair. Other than that, we have used an LED along with a current limiting resistor, a variable resistor, and a thermistor. Thermistors are used to limit the passage of current through them according to the temperature. When the temperature is low, they have higher resistance, and as the temperature increases, their resistance starts decreasing, allowing the current to flow. Both the transistors are BC547. These transistors are NPN bipolar junction transistors. They are mainly used to amplify the current. A small current at its base controls a large current at emitter and collector terminals. The working of this circuit is simple. It is operating at 9 volts. Initially, when there is no heat, the circuit will remain turned off. When the thermistor receives heat, its resistance will be decreased and it will let the current flow. This will activate both the transistors and the voltage will be passed to LED and it will light up. A variable resistor of 20k ohms is used to adjust the circuit for activation of LED on the required temperature or heat. This device is ideal to use where you don't want any device or equipment to be overheated. The circuit is compact, so it can fit anywhere. For example, using as fan flow controller to keep the board cool. Inrush current limiter in power supply boards. And battery circuit breaker when heating the battery. What is a PTC thermistor? Sensor or thermal resistance with positive thermal coefficient, PTC, full name, positive temperature coefficient. Unlike the NTC thermistor, this thermistor has a direct relationship with temperature. That is, it is a resistance with temperature which increases with the highest temperature. Most circuits use NTC thermistor, but PTC thermistor can also have important applications in power supply designs. If we use PTC instead of NTC in the previous circuits, the circuit will work the opposite way. The work of this circuit is simple. It works with a voltage of 9 volts. Initially, when there is no heat, the circuit is on. When the PTC thermistor receives heat, its resistance increases and disables the circuit. This both disables the transistors and cuts the voltage to the LED and turns it off. A 20k ohm variable resistor is used to set the circuit to disable the LED at the required temperature or cold. Ideal for use where you don't want any device or equipment to overheat. The circuit is compact, so it can be placed anywhere. For example, use of PTC thermistor to reduce inrush currents, to start industrial engines, to protect industrial engines, for self-regulating heaters, and for electronic thermostat of refrigerators and coolers. Light-dependent resistors, LDR, are also known as photoresistors. They are made of high-resistance semiconductor materials. When light hits the device, photons energize the electrons. This causes them to jump into the conductive strip and thus conduct the electric current. How the LDR circuit works. When it's dark, the LDR has high resistance. This makes the voltage at the base of the transistor too low to turn the transistor on. Therefore, no current will go from the collector to the emitter of the transistor. All the current will instead pass through the LDR and the potentiometer. When it's light, the LDR has low resistance. This makes the voltage at the base of the transistor higher, high enough to turn the transistor on. Because the transistor is turned on, current flows through the transistor. It flows from the positive battery terminal, through R1, the LED, and the transistor down to the negative battery terminal. This makes the LED light up. Resistor R1 controls the amount of current passing through the LED. Its calculation is simple. I made a video on how to calculate the resistance value for an LED, which you can see on my YouTube channel. If you are using an LED with 2V voltage drop, you will have a 7V voltage drop over the resistor when the transistor is on. By using Ohm's law, we can find the current. An 18 mA is usually a good current value for common LEDs. The variable resistor R2 is used to change the trigger point for the LED. That is, how much light that is needed for the LED to turn ON and OFF. You can probably replace it with a 10 kilo-ohm potentiometer. It depends on the resistance of your LDR. But with a 100 kilo-ohm potentiometer, you will have room for a wider range of LDR values. A circuit that detects darkness or a lack of light is known as a darkness detector or dark detector. In this project, we've used the LDR, the most basic of all light sensors, to construct a straightforward darkness detector circuit, light-dependent resistor. These darkness detector circuits can be utilized in systems that switch on lights automatically when it becomes dark. Some parts are passive, such as capacitors and resistors. LED has been used as an alarm to signal nighttime. This straightforward project's goal is to use an LDR to detect darkness and an LED to illuminate it. The LDR's resistance decreases dramatically in the presence of sufficient light. Under these circumstances, the voltage divider created by the LDR and 1 kilo-ohm resistor will output almost 0V. You won't see any output at the transistor's output pin as a consequence. The amount of light shining on the LDR will be reduced if we obstruct it with a hand or other object. The LDR's resistance will rise as resistance does. The light detection will work since an LED was attached to the transistor collector output pin. As a result, the LED will be off while there is sufficient light on the LDR, and it will turn on and shine when it is dark. In this section, we will examine the humidity-sensitive circuit. This circuit is versatile and very sensitive. It can be used to detect moisture in substances like floors, walls, soil, etc. Normally, in moisture sensor circuits we use one transistor, but in this circuit, we are using two transistors to increase its sensitivity. The circuit is simple and inexpensive because it uses only a few components. A resistive sensor is used to detect humidity. 22N4401 transistors or any NPN transistor with the same specifications are used to act as switches. A variable resistor is used to set the desired humidity level at which you want your relay to activate. The operating voltage of this circuit is 9 to 12 volts DC. When the humidity-sensitive resistor, HSR, detects moisture in a material, its resistance decreases and cuts the base voltage of transistor Q1, turning it off. Now, the base Q2 is activated by the 1 kilo-ohm resistor and turns on. This will activate the relay, and whatever equipment connected with your relay will start operating. But when there is no moisture, the HSR ohmic resistance is high and is on through the current flowing through the variable resistor to the base of transistor Q1, so it gives 0 V at the base of transistor Q2 and is off. This will disable the relay, and any device connected to your relay will be turned off. We have used a 50 kilo-ohm variable resistor to adjust the sensitivity of the circuit. You can transform this circuit into an alarm visual indicator by connecting a buzzer or an LED instead of a relay. The relay should have the same voltage as the input voltage. This circuit can be used to detect moisture in different substances such as your plants, soil, wood, containers, etc., and after detecting the moisture it will switch on your desired equipment. For example, it can turn on a fan to dry some moisture from any substance. And also, automatic plant irrigation systems, plants in your house, greenhouse projects. The MDR sensor has a direct relationship with the magnetic field. That is, it is a resistance with a magnetic field, and the value of this type of resistance changes in the presence of a magnetic field. As the magnetic field increases, the resistance value increases, and as the magnetic field decreases, the resistance value decreases. We can design two types of circuits for it. The first circuit turns on the LED by approaching the magnetic field and vice versa. The second circuit turns off the LED when approaching the magnetic field and vice versa. Each of which will have its own users. For example, suppose you stick a magnet to the door. When the door is closed, the LED is off because the sensor is near the door, but when the door is opened, the LED is off, or vice versa. Instead of LED, an audio warning alarm can be installed. When the magnetic field is high, MDR has high resistance. This causes the base voltage of the transistor to be too low to turn the transistor on. Therefore, no current will go from the collector to the emitter of the transistor. All the current will instead pass through the MDR and the potentiometer. When low, MDR has little resistance. This causes the voltage at the base of the transistor to increase, high enough to turn on the transistor. Because the transistor is turned on, current flows through the transistor. It flows from the positive battery terminal, through R1, the LED, and the transistor down to the negative battery terminal. This makes the LED light up. If we replace MDR with resistor R2, the circuit works in the opposite way. MDR sensor has a direct relationship with the magnetic field. That is, it is a resistance with a magnetic field, and the value of this type of resistance changes in the presence of a magnetic field. As the magnetic field increases, the resistance value increases, and as the magnetic field decreases, the resistance value decreases. We can design two types of circuits for it. The first circuit turns on the LED by approaching the magnetic field and vice versa. The second circuit turns off the LED when approaching the magnetic field and vice versa. Each of which will have its own users. For example, suppose you stick a magnet to the door. When the door is closed, the LED is off because the sensor is near the door, but when the door is opened, the LED is off, or vice versa. Instead of LED, an audio warning alarm can be installed. When the magnetic field is high, MDR has high resistance. This causes the base voltage of the transistor to be too low to turn the transistor on. Therefore, no current will go from the collector to the emitter of the transistor. All the current will instead pass through the MDR and the potentiometer. When low, MDR has little resistance. This causes the voltage at the base of the transistor to increase, high enough to turn on the transistor. Because the transistor is turned on, current flows through the transistor. It flows from the positive battery terminal, through R1, the LED, and the transistor down to the negative battery terminal. This makes the LED light up. If we replace MDR with resistor R2, the circuit works in the opposite way. Reed switches are a special kind of electrical switch, actuated, turned on and off or changeover by magnetism. The most common type features two thin, flexible, ferromagnetic metal wires or blades, the reeds, positioned slightly apart in a hermetically sealed glass bubble. Unlike MDR, which has a wider resistance range, reed switches only In this part, I am going to show you how to make a simple IR LED detector circuit. IR sensors can detect a wide range of physical properties such as temperature, motion, and proximity. In complement with IR receivers, these are commonly used as sensors. The appearance of an IR LED is the same as a common LED. An IR sensor can measure the heat of an object as well as detects the motion. Usually, in the infrared spectrum, all the objects radiate some form of thermal radiation. These types of radiations are invisible to our eyes, but infrared sensor can detect these radiations. When IR light from a fire falls on the reverse-biased photodiode, a current flows through it. This triggers the base terminal of the transistor. The BC547, which was previously off, switches on and starts conducting current between its collector and emitter terminals. This current also flows through the buzzer, producing an alarm and triggering the LED to glow. The LED resistor pair is there to add a light indication in addition to the sound from the buzzer. If you want to keep the circuit simple, feel free to skip it. The photodiode is very similar to the phototransistor. They are both light trigger devices that are connected in the same way in a circuit. The difference is that a phototransistor is a transistor with a photodiode connected to its base. When light hits the photodiode, current flows through the base, and the transistor turns on so that current can flow through it. Here we use a microphone as a sound sensor to detect sound in the frequency range of human hearing. A microphone is a device that translates sound vibrations in the air into electronic signals. With this sound-activated switch, control by sound may be very useful, not just on a robot, but also for a bit of home automation, for example a sound-activated light responding to a knock on the door or a hand clap. The light will be automatically switched off after a few seconds. An alternative use is burglar protection. If someone wants to open the door or break something, the light will come on, suggesting that someone's at home. When someone claps, the microphone captures the sound and converts it into an electrical signal. This weak signal is then sent to the base terminal of the transistor through a coupling capacitor. Transistors are essential in amplifying weak signals, a function demonstrated in this project by utilizing two transistors. Microphone operation. The electret microphone generates a small AC signal voltage in response to sound waves. The AC component of the signal is superimposed on a DC bias voltage. First transistor, common emitter amplifier. The first transistor amplifies the weak AC signal from the microphone. The base current of this transistor is controlled by the AC component of the microphone signal. Second transistor, emitter follower. The amplified signal from the first transistor controls the base current of the second transistor. The emitter follower configuration provides high input impedance and low output impedance, making it suitable for driving low impedance loads like LEDs. LED indicator. The LED lights up in response to the amplified audio signal. The LED and its current limiting resistor form a simple visual indicator of the amplified signal's presence. Resistor, 5.6 kΩ. This resistor biases the electret microphone. It provides a stable biasing voltage for the microphone, ensuring proper operation and signal output. The value of this resistor often chosen based on the specifications of the electret microphone. Capacitor, 10 microfarad. The capacitor connected in series with the electret microphone. It acts as a coupling capacitor, allowing the AC audio signal from the microphone to pass through while blocking the DC bias voltage. Transistor 1, BC547. The first transistor configured as a common emitter amplifier. Moreover, it amplifies the weak audio signal from the microphone. The base current of this transistor controlled by the microphone output. Resistor, 1 megaohm. This resistor provides additional biasing for the base of the first transistor. It helps in stabilizing the operating point of the transistor. Resistor, 100 kΩ. This resistor connected to the collector of the first transistor. It provides a load for the transistor and also forms a voltage divider with the collector-emitter path of the first transistor. Transistor 2, BC547. The second transistor acts as an emitter follower. It provides impedance matching and additional amplification for the signal. The collector current of the first transistor controls the base current of the second transistor. Ultrasonic alarms receive high-frequency sound waves that are not audible to the human ear, but can be used to detect the presence of objects or movements within a specific range. These alarms are widely used in various applications, such as security systems, industrial automation, leak detector, and robotics. In this part, I will show you how to build a simple ultrasonic alarm circuit that can detect the presence of objects or movements within a specific range and trigger an alarm. The circuit has a 40 kHz ultrasonic receiver RX, which is connected to the base of T1. It is a common emitter amplifier, which amplifies the signals received by the RX. The amplified signal available from the collector of T1 is coupled via C1 to the signal detector stage comprising T2, D1, and C2. When RX continuously receives the ultrasonic, T3 remains saturated and conducts. This keeps T for output conduction since its base is at ground potential. When the ultrasonic beam breaks, T3 turns off and T4 conducts. The piezo buzzer connected to the collector of T4 sounds the alarm. Red LED indicates the standby mode, showing that the alarm system is active. A gas sensor is a system that senses the presence or concentration of gases in the atmosphere. By changing the resistance of the material within the sensor in response to the gas concentration, the sensor generates a corresponding potential difference, which can be calculated as output voltage. As we can see, there are two different circuits inside the sensor. On the one hand, there is a heating circuit between points H of the diagram. On the other hand, the circuit between points A and B is used to measure the resistive change of the sensor due to the presence of the gas. A wide range of these types of sensors is sensitive to different gases naturally present in our environment. The pins can be connected either way round, as they does not have polarity. The heater pins are named as H each. While the pin XX is connected to VCC, the pin YY is connected to the base of the transistor BC548. The heater pins can also be interchanged. The preset resistor is used to set the sensitivity. The gas leakage alarm circuit uses a BC548 transistor to turn on the buzzer whenever LPG gas is detected by the sensor. Initially, when the circuit is turned on, the coil inside the sensor starts heating up and the current flow through the coil is controlled by a 33 ohms resistor, while the Zener diode makes sure that the voltage flow does not exceed 5.1 volt. The XX pin is connected to the plus VE of the power supply via a resistor, while the YY pin is connected to the base of the transistor BC548. The 100 kilo ohms preset resistor is used to set the sensitivity. When the gas concentration in the air increases, its output goes high and it makes the transistor to trigger the buzzer and a LED. The buzzer and the LED remain powered until the concentration in the air decreases below the specified level. Setting and testing the circuit. After completion of the making of circuit, take it near the LPG gas stove and switch on the power supply. Make sure that there are no flames or electrical devices that could cause sparks in the vicinity of the stove and the circuit. Now, turn on the gas stove without lighting it and adjust the preset using the screwdriver so that the buzzer rings only when there is reasonable gas concentration in air. After the adjustment is over, enclose the circuit in a suitable casing and install the sensor nearer to the gas stove. Make sure not to include any electromechanical devices in the circuit, as the sparks that might be produced while they are working could cause fire when there is a gas leakage.